Reinforcement learning. Unlike supervised and unsupervised machine learning algorithms, reinforcement learning does not use initial data to train. The learning model is given an objective and definitions for the successful achievement of the goal. The model then iterates through actions and through trial and error, learns how to best achieve the goal. The model consists of an agent, computer program, performing actions which are based on defined success criteria. The agent is rewarded for correct steps and penalized for incorrect steps until eventually an end state is reached. Several use cases include manufacturing automation, stock market trading, robotics, and self-driving cars. For example, let's train a model car to navigate to the finish line of a track. The model car, the agent, sits on the track, the environment. Its action choices are to move forward, turn left or turn right. The car monitors what it can see of the track, the observation, and chooses to move forward, the action. This leads the car to a position on the next section of track. The car determines if it is still on the track, its state, and is given positive or negative reinforcement, the reward. For each new state, the agent must observe and act until it crosses the finish line. As the agent is being positively rewarded, it is incentivized to continue that action during that specific state. The agent continues this process for the duration of an episode being a collection of environment, state, action, reward and observation information that occurs between a start state and a termination state. This methodology is called the Markov decision process. Compared to supervised learning where existing labeled datasets are used to predict outcomes, for example, training a model to detect automobiles, and unsupervised learning where unlabeled data with similar characteristics is clustered based on patterns, for example, detecting shopping patterns and offering product suggestions, reinforcement learning requires no initial data input or labeling, making setup easier and less time-consuming. Also, since there is no initial data, reinforcement learning tends to be less susceptible to bias and less computationally complex. Amazon SageMaker RL builds on top of Amazon SageMaker, adding prepackaged reinforcement learning toolkits and making it easy to integrate any simulation environment. Training and prediction infrastructure is fully managed, so that you can focus on your RL problem and not on managing servers. Users can deploy containers provided by SageMaker for Apache MXNet and TensorFlow or create their own custom environments. Some popular algorithms used in RL include Monte Carlo, Q-learning, DQN, and proximal policy optimization PPO.